Hello everyone, this is video 2.2 on defining fractions. I should probably explain, there's no video for 2.1. You should probably look over it, you should probably read it. It's not that it's not important, it's on problem solving and explaining solutions, and there's a lot of valuable information there, but it's just not something that I don't think, or I don't know that I can necessarily add anything to what's there. So if you would like, have a quick read through, but I'm not going to do a separate video on that. So let's get started with 2.2. So the first thing is we need to do some definitions whenever we start a new chapter or a new unit. It's always a good thing to sort of define our terms. And in chapter 2, we're going to be talking about fractions, the bane of many students' existence, or so they think. When we're talking about a fraction, we're only talking about two things. We're talking about the number of parts that we're taking, and then we're talking about the number of equal sized parts that form that whole. And during this chapter, you're probably going to get tired of me really overemphasizing the term equal size. Um, but it's a crucial part of understanding about fractions. And it's something that when students make a mistake around, it can really lead to a lot of mistakes, a lot of misconceptions, a lot of errors on the parts of students. So the equal size part is a pretty important part. Um, so we are uh, going to, let's look at a fraction here. So let's say that we have the fraction 2/3. So this 3 lets me know that my whole is broken into 3 equal parts, and then I want 2 of those. Now, what the whole looks like, we'll talk about it here in a moment, and which 2 of those 3 we choose, it doesn't matter. But we have a comparison here. We have the number of parts, the 3 is the number of parts, and then the 2 in this case is the number of parts that we're going to choose. Anytime we have a fraction where it's 1 over something, like 1/3, we call that a unit fraction, and this is where we just have one part of that whole. Now, later on, we're going to get to operations with fractions, and especially when we start talking about dividing with fractions, this idea of a unit fraction is going to be pretty important. Unit fractions, in a lot of ways, are going to be easier to work with because the one uh, typically gives us one less step in our operations. So if you're doing something with students and you find that they're having a lot of difficulty working with non-unit fractions, um, dial it back a step and have them go through the same sort of process or the same operations with a unit fraction and see if that works. And if not, then you need to go back a little bit further. And if so, then you can kind of start to isolate where the misconception is, where the errors are. But so yeah, a unit fraction is where we're taking one part. Um, and so we've got our fraction a over b, which we looked at already here. We know we have a equal size parts. This is my a over here, and then b equal size parts. What I really want you to think about and really focus on, I think the mistake that a lot of teachers make is when they talk about fractions, they just say, well, a fraction is a number over a number, or a fraction is a numerator over a denominator. And so you're describing the symbol, you're describing the numeral rather than talking about what a fraction is numerically. Like, what does it mean as a quantity? And so the idea that it's one number over another number, that's what it looks like. I mean, that's how you can spot it in the wild. But it doesn't really help you understand what it means. It doesn't really give students any insight into what it actually does, why it's needed, why it's important. And so when we don't build any sort of like concept around the idea, even starting with the definition, we really put students in a bad position to be able to work with these things when it's time to do operations with them. Okay, so I was trying really hard not to use these words on the previous slide because I knew I was going to be defining them here on this slide. So let's talk about numerator and denominator. And so you see the definitions that I have here, that we're talking about equal sized parts that we've selected, and then how many of those parts go toward our whole. You'll notice that I've avoided using two really common words that teachers use when talking about this idea, and that is I'm not saying anything about top, and I'm not saying anything about bottom. And the reason is because when you just say, well, the numerator is the top number, the denominator is the bottom number, like I've already mentioned, and I'm going to really belabor this point because I think it's a really important point when teaching about fractions. Saying top and bottom doesn't really describe anything that's going on with the actual mathematics. It lets me know what it looks like, it lets me know how to identify it, but it doesn't tell me why it's doing what it's doing. There's no reason why the numerator couldn't be on the bottom. There's no reason why the numerator couldn't be on the side. There's no reason why the numerator couldn't be in front. I mean, like, you can put the numerator wherever you want. The top and bottom is just the way we've agreed to do it. But the concept, the idea is something greater than that, right? So it's really easy to lean on this symbolic definition of what they mean, but that symbolism doesn't really describe the mathematics. So we really want to try to avoid that as a definition. You can use that to describe it. Well, the numerator is the top number, which is also the number of equal sized parts. Or you say, well, the numerator is going to tell us how many parts we're selecting, and we write that as the top when we write it like blah 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 blah. So I mean, it can be part of it. So I'm not saying that you never want to say that it's the top number of the fraction, but just don't limit yourself that it's the top number of the fraction, right? So it should be the secondary part of the definition, not the primary or sole part of the definition. I wanted to look at a quick example about this. So we've got a rectangle here. It's a 5 by 4, so there's 20 x's that are there. And I want to do this problem in fifths. So I want to break this thing into 1/5 size pieces. And so we have a student who's going to break these down like so. So we've got a student that's going to break down, say, 1, 2, 3, 4. And let's see, we've got 1, 2, 3, 4. We've got 1, 2, 3, 4. We've got 1, 2, 3, 4, and 1, 2, 3, 4. And so fifths, so there should be 5 pieces. There's 1, 2, 3, 4, 5. So students broken these down into 5 equal sized pieces. Now, don't get hung up that equal size means equal shape. Now, it's going to be a little bit easier probably for you and probably for a lot of students to just go through and say, okay, well, here, there's 1, there's 2, there's 3, there's 4, and there's 5. And just put these horizontal lines in and break it into equal parts that way. It's probably easier to draw, it's probably easier to see, it's probably easier to understand if all the parts are the same shape. But there's no requirement that they are. And in this area model, there's a lot of flexibility and a lot of creativity to how we think about 1/5. Each one of these pieces in the dark blue answer, they all contain 4 x's. And so they all contain 1/5 of the larger rectangle. So when we're talking about equal size in this definition, we're talking about the number, not necessarily the shape. Not necessarily, I mean, the size, the area will be the same because they all have 4 x's in them. But, without getting into too much of the geometry, the perimeter isn't necessarily the same for all of these. So there's some differences in what's going on here. But we're talking about how many x's are in there, not necessarily the shape. If you want to break them all into rectangles, man, that's cool, but it's not an obligation in this problem. So I've already kind of looked at one model for this, but there's a lot of different models that you can use for fractions. And as a teacher, it's good if you can be flexible in which models you use. There's going to be cases where a number line is going to be a more reasonable model. There's going to be cases where a rectangle is going to be a more reasonable model. There's going to be cases where a circle is a better model. So if you just have one model, then you're always going to be using it. And the old phrase, if all you have is a hammer, everything looks like a nail. If all you have are circular models, then you're going to be really limited. In class, I like to use a polygon model, and I'll see if I can find a link to a pattern block fraction activity. But there's a lot of different ways we can think about how to show and express and work with fractions. So I just wanted to look at, for a moment, how we can kind of use all three of these models to sort of show um, ideas around fractions. So when we're talking about number lines, and so typically with a number line, we're going to break this from 0 to 1. And then what we understand from this is that, again, these have to be equal sized parts. You're going to have some students who are going to want to break this like this and call these thirds. And so you're going to have that discussion again, that equal size part, that this part, and this part all have to be the same size. And so one of the ways that I like to talk about this with students is to appeal to their sense of fairness. That if I break this into thirds, you should be happy with any of the pieces that you get. So if this were a candy bar, which I recognize now becomes an area model instead of a linear model, but whatever. And we were to break this into 3 parts. Would you be happy if you got any of those parts and your friend got a different part? And and students would be like, well, no, I want this part. The fact that there's a part that you want pretty much lets you know this is not broken equally. It's a good indicator that they're not broken into the same size. So we want to make sure these are all broken into the same size pieces, and students recognize that. So this is broken into 4 parts. So I recognize that this is broken into fourths. Some of you are probably really bothered that I wrote 2/4 and you want me to write 1/2. I mean, you can replace this with 1/2. But because we're breaking this into fourths, I wanted to really lean on the denominator being a fourth. And so now I can shade this in and show that this is 3/4. Where does the 4 come from? Well, I've broken it into 4 equal sized pieces. Where does the 3 come from? I've selected 3 of them. And that's it. That's the whole thing. And so as a linear model, as a number line model, this is how I'm going to show 3/4. As a rectangle, for reasons that'll be obvious in a little bit, I want to break my rectangles all going kind of the same direction when I'm building these models. Now, this may seem a little bit contradictory to what I just said in the previous slide, where you can break into a whole bunch of directions. It's not contradictory because I'm not saying that you can't do that. I'm saying that I want to try to limit it this way because I'm going to want to use this vertical horizontal breaking later on to a certain effect. So there's nothing wrong with doing it that way, but it limits your ability to do a certain type of problem, a different kind of modeling a little bit later on. So it's not incorrect to do it. I just don't want to do it for this problem. And so here, I'm going to break this into fourths. And then I'm going to shade in 3 of them. And so now this shows 3/4. And some of you might be looking at this and saying, well, if I just take this number line and extend it up, I get this area model. And you're correct. I mean, all of these, I mean, they're not identical, but all these models should rhyme. I mean, they should all have a common theme to them because they're all showing the same thing. They're all showing 3/4. As a circular model, I'm going to draw a circle, or I mean, let's just pretend that's a circle. And I'm going to break this into 4 equal sized pieces and then shade in 3 of them. Now, the limitation for me with circles is getting students to being able to draw thirds, fifths, sevenths on a circle is an absolute pain in the neck. And it almost feels like you're just being cruel, like you're being mean to students, trying to get them to break into sevenths. And I'm not going to lie, even as a teacher, drawing a circular model using sevenths is not fun. It's not very easy. So I see teachers sometimes who are really limited, like they really want to use circular models, and then when they get to a problem like like sevenths or ninths or even fifths, it's a real challenge. Also, be aware that you're going to have some students for circular models who are going to want to break it into fourths like this. And there's an interesting, probably geometry or even calc problem around where to position these lines so they are equal size, but that's not what we're doing in this class. So you would have to have a conversation with a student about why this doesn't work. And clearly because this piece is a whole lot bigger than this piece. And so if they're used to doing these rectangles and being able to draw these lines that are equally spaced, and that's going to make equal sized parts, well, why wouldn't it work for the circle? I mean, it's a different shape, it's a different model. So there's some explanation around that as to how we would want to do that. And then there's other sort of like irregularly shaped models. So we could draw triangles, 1, 2, 3, 4, like that, and then shade in 3 of those 4. And so you have these sort of polygon models that you can use as well. And when you're using certain manipulatives and students are putting those pieces together, then you can have them talking about fraction, not using sort of a standard model, especially for older kids that are going to be really locked into rectangles or circles or whatever sort of model that they're working with, to really get them thinking flexibly about what a fraction is and how to model fractions, having them use different polygons like triangles, like rhombuses, is going to really give them the opportunity to show a lot of flexibility and fluency around how they think about fractions. So we should also talk very quickly about proper and improper fractions. So a proper fraction is going to be any fraction that is less than 1. And then an improper fraction is going to be anything that is greater than or equal to 1. Now, again, we're going to try really hard not to lean on too much this idea that a proper fraction is where the numerator is smaller, or that an improper fraction is where the numerator is greater. We can talk about that, but really I want you to think about the effect of that, what that does mathematically rather than what it does symbolically. So a proper fraction is going to be less than 1, improper is going to be greater than equal to 1. Now, what I think is really interesting about these, and the way I learned these, was just, well, the numerator is bigger, the numerator is smaller, and then maybe a little bit that's greater than equal to 1. But I never really experienced learning this as a child, what that meant in terms of the model. So I'll give you an example. So let's say that I have a rectangle model. So we'll go back to the rectangle that we were looking at before. So I'm going to break it into fourths. And let's say that I wanted to model 5/4. So how am I going to model that? And this can be really kind of a tricky thing to show to students, because as soon as you add on this fifth piece, and now it looks like you're working in fifths instead of fourths. So how do you show that you're taking 5 pieces when you want 4 pieces to be the whole? So there's a couple things you can do to make this work for this model. And one thing you can do, which is really never a bad idea, is to sort of like put this piece in here that says that 4/4 equals 1, or to say that this is my whole. And then once you've indicated what the whole is in your problem, now you can be a little bit more flexible with it. I also think it makes a little bit more sense when you're adding that fifth piece to put a little space in here and not directly attach it. So 4 of these pieces make a whole, and then I have this fifth piece. So how many pieces do I have? Well, I have 5 of them, so I can shade these in. So here's 1, 2, 3, 4, 5. So I have 5 pieces, and 4 of them went to make a whole. This is probably a little bit easier to show on a number line, where we'll go here, 1, 2, 3. So I got 0, and then I have 4/4 equals 1. And so you'll see it's the same idea. I'm still showing where my whole is, and I can see that there's 1, 2, 3, 4 parts that go to make that whole. And now I just want to ask, well, where is this point? So that's 1, 2, 3, 4, 5. So this would be 5/4. So you can see these two different models show this idea of 5/4, this improper fraction, in a very different way. And so for some students, this area model might make more sense. In others, this linear model might make more sense. So if you've got more varied and more flexible tools that you can use in your class, the more students you're going to be able to reach, and the better you're going to be able to sort of illustrate these ideas, these concepts.
So here's a checkpoint problem I want you to think about, and like always, we can talk about it in class, or we can talk about it in office hours or whatever. But this is 2/3 of an original rectangle, and so what do we know about that original rectangle? So I want you to really think about what the 2/3 means, and in this piece, how do we represent the two? What do we know about the three? And what does it tell us about this rectangle versus the original rectangle? So I'll leave this problem for you to look at and to think about. So yeah, thanks.